A special type of equilibrium constant can be used for complex ions. It's called a formation constant, and it's given the symbol K sub F. Now, a formation constant is specific for complex ions, and a formation constant, you put whatever goes into the complex ion as reactants, and the complex ion itself is the product. So you can see for that CuNH3 2 plus thing, this would be the form. So products over reactants, the Kf, which is down here at the bottom, would have copper NH3 2 plus on the top, divided by copper 2 plus, divided by the ammonia to the fourth power, which is pretty crazy. Now, these Kf values, these formation constants, are usually incredibly product favored. Ks are usually much, much, much greater than 1. And that just shows that, boy, they are ready to go. So if you have a little copper 2 hydroxide and you add too much hydroxide or ammonia, this thing is going to kick in big time because it's so product favored. So you're going to see this reaction pretty readily. So the important part here is that if you see a formation constant, the complex ion is the product in the numerator, and in the denominator you have whatever goes into the complex ion. So in this case it would be copper 2 plus and ammonia to the fourth power. Cool. In the Le Chatelier's principal lab, we experienced the ZnNH3 2 plus complex ion. It's something that happens. There's also a somewhat common AgCN2 1 ion. Lots of these different things running around. But again, the important part is that the metal will be the Lewis acid, and the bases will be something with lone pairs that are pushing themselves in. So ammonia is a great Lewis base. It's got the nitrogen on it with a lone pair like we talked about. Cyanide is a great Lewis base. Both this carbon and the nitrogen, if you draw the Lewis structure out, have lone pairs. So there's lots and lots of lone pairs kind of running around there. If you wanted to write a formation constant for the AgCN2 1 ion, this is what it would look like. Again, the complex ion is the product, and the ions that go into it will be the reactants. So Ag plus and 2 cyanides, while the product will be the complex ion. Kf here will be, again, complex ion on top, the ions that go into it in the bottom. So AgCN2 1 on top, silver plus on the bottom, Cn 1 on the bottom, squared. Kf comes out to be 5.6 times 10 to the 18th. Again, super product favored. These things are ready to form at just about any notice and stuff. Yeah, very, very large. Expect a complex ion, basically, if you know it's out there. This is a table showing some respective Kf values, and again, you can see they're kind of all over the place. But all of them big. These are all numbers greater than 1, and you can see some of them are quite a bit greater than 1. All of these, to write the expression, the ions that go into it will be the reactants, and the complex ion will be the product. And these are usually written as net ionic reactions. Like, you're not seeing the counter ions. Like, for example, in the AgCN2 1, the silver plus would probably be like silver nitrate. And I would guess the cyanide would probably be a sodium cyanide. But you're not seeing the nitrate or the sodiums. They're spectators and honestly pretty boring to chemists. So that's why they're not usually shown in these kind of contexts. You can use these in some kind of clever ways, however. Silver chloride is a compound that actually will coat glassware once it's formed, and it makes kind of a fuzzy white look on some of the glassware, and maybe you've seen it this quarter in our labs. If you want to get rid of that silver chloride, you can scrub the heck out of it, but you can also use a chemical method, because if you add some ammonia to the silver chloride, this complex ion, AgNH3 2 plus, will form, as well as some chloride. So this is actually a pretty cool way to get rid of some of that nasty white stuff. Now, if you want to see exactly what's happening, here's the KSP for silver chloride. And remember, KSPs, this precipitate is the reactant, and the ions that go into it are the products. This KSP is much less than 1, means there's silver chloride solid's going to form really readily. No problem. You can combine this with the complex ion, the AgNH3 2 plus. Now, this Kf value, 1.6 times 10 to the 7th, you can add them together. Silver plus 2 ammonias making complex ion, as well as the KSP expression. And I bet you can maybe see where we're going here. We're going to add these two expressions together. We're going to ditch the silver. Silver plus is a product in the first one, and it's a reactant in the second one. So if you get rid of those and add them together, you get silver chloride plus 2 ammonias making the complex ion AgNH3 2+ and chloride. And then K net for this one would be literally KSP times KF. When you add reactions together, you multiply the Ks. This comes out to be 2.9 times 10 to the minus 3. So even though it's still reactant favored, it's much less reactant favored than the KSP for silver chloride. So it's much more likely to get rid of the silver chloride by adding ammonia than if you don't add the ammonia. So this is kind of a positive use sometimes if you want to have cool glassware. And of course, that's what we try to do here at Mount Hood.
When solutions of silver nitrate and sodium chloride are mixed, insoluble silver chloride precipitates from solution. When we add ammonia to the mixture, however, the precipitate redissolves. When ammonia is added to a mixture of solid and aqueous silver chloride, the ammonia serves as a Lewis base. The complex ion formed consists of 2 ammonia molecules bound to each silver ion. Formation of the complex lowers the concentration of silver in solution, which changes the solubility equilibrium.
So it's not that the ammonia will get rid of all the silver chloride. Like you can see in the video in the bottom, there is still some solid AgCl left around, but it does a great job. All right, the ammonia again acts as a Lewis base. It attacks the silver of the silver chloride, the Lewis acid, and it's able to remove the silver as the complex ion from the silver chloride, which is really, really cool. So it will get rid of your pesky AgCl if it's coating your glassware. Kind of a cool thing. Ammonia can be all right. This is called coupled equilibria, by the way. The book uses this term, and it just means you're adding 2 reactions together. And almost always you're going to cancel one of the chemicals, like we canceled silver here. If you need to calculate the new equilibrium constant, you would multiply these Ks together to get the new value. Remember that if you flip a reaction around, you can go 1 over K to get the new value of that. Pretty chill. Here's another example of coupled equilibrium. We saw the formation of ZnNH342+ in the Le Chatelier's principal lab. So if you're curious about that, anyway, you can use the KSP for ZnOH2, zinc 2 hydroxide. It breaks down to zinc 2+ and 2 hydroxide, the KSP 4 times 10 to the minus 17th. Well, if you do the same thing like we did in the last one, zinc and ammonia make this zinc NH342+ complex ion. There's the KF value for that one, 3.6 times 10 to the 8th. Now again, coupled equilibria just means you're combining 2 or more reactions to give some desired third reaction. We'll couple these 2 together. We'll be able to cancel the 2 zinc atoms, and you can see then that zinc hydroxide plus 4 ammonias makes the complex ion plus 2 hydroxides. K net, the K of this overall reaction, will be KSP times KF, 1.4 times 10 to the minus 8th. So again, still reactant favored, less than 1, but certainly not as reactant favored as the KSP value. So it makes it more soluble than it was before, which is kind of cool. This can be used to explain why hydroxides dissolve in acids. There's all kinds of kind of cool things you can do here with common ion effect. So anyway, common ion effect in some ways is just Le Chatelier's principle too. You can decide the best way that all this works out. But anyway, as long as you understand the idea of combining reactions to get some overall desired reaction, and you can multiply the Ks together to give the overall K, you are good to go.